Hello everyone, my name is Stacy. I represent database marketing. Welcome to our webinar, Designing a Schema for a Data Warehouse. Please be aware that we'll share all webinar materials with you by email within a week or so after the webinar is over. You can ask and answer questions during the webinar using the corresponding tab, the Q&A tab. And there will also be polls. You will answer them. They are pretty intuitive. And our today's speaker is Federica Razzoli, founder and chief database expert at Database. So, hello, Federica.
Hi, Stacy, and thanks for your introduction.
Ready to take the virtual stage?
Sorry?
Are you ready to take the virtual stage?
Yeah, absolutely.
Perfect. Let's start.
Can I start? Cool. Perfect. Then I'm going to talk to you brave people about a brave topic, because this is a big matter, actually. I would love to read from you guys if you can write in the chat why are you interested in this. If you already have a data warehouse, for example, or if you are going to build one, or if you are just considering it. Anyway, so let's start by answering this simple question: why a data warehouse? Well, this is the typical situation of a company. Right? Data is a mess if you look at it globally, because you have it shattered over multiple technologies, very different from each other. In this example, I've put Postgres, MariaDB, Mongo, and Oracle logos. And well, it's not uncommon, actually. Oracle sometimes is used for some particular CRMs. Maybe MariaDB is used for some applications, Postgres for some others, and so on. And of course, we also mix different data models, right? Relational, documental, key value, and whatever. So basically, this means again that data globally is a mess. Okay, different databases. Then we have some data for internal applications by some, stored in some databases that we normally don't look into. Then we maybe have some SaaS applications that we use online, such as Salesforce or Slack or whatever. And the latter two can be accessible via APIs or via downloadable files. The first category is hopefully accessible via SQL, but not always. It depends what database it is. And to sum up, this means we have different wired protocols, different query languages, different schemas that are methodically not documented. So you have to find out what various tables mean. And they are designed to retrieve a single row fast, or more generally, to answer OLTP-like queries, but not for analytical aggregations, which need different data structures and different indexes. And of course, the technology itself, the database technology itself that is used is not designed for OLTP. It is designed for OLTP, so it will be fast for OLTP, hopefully, but it won't be fast at all for analytics. And then our data could be conflicting with each other, redundant, incorrect, missing. So actually, I won't dig into this, but of course we should also work on the data quality when we move it from its original sources to the data warehouse. But again, I won't dig into this because it's a completely different matter, but it's something you should keep in mind. And then, of course, the business metrics are in this data if you know where to find it, but also personal information is in this data, and data analysts shouldn't have access to this information without a good reason. Otherwise, you will be breaking some regulations. Okay. So instead of this, what you want to do is, well, analysts should connect to a single database and run SQL queries. And the schema of that database should be standard, meaning that it should be designed with a technique that is rock solid and used by a lot of companies for many years. And it should be, of course, designed for analytical queries, and it should run on a technology that is designed for analytical queries. Okay. So, for example, maybe MySQL is great in terms of performance when it comes to OLTP, but it's terrible when it comes to analytics, right? Well, actually, one more word about this. You should, as I said, use a relational database for the data warehouse. Well, not just should, you have to. But it can be also a columnar database, and there are many good reasons for this. I will mention some of these reasons when I show you some examples of how data can be stored. But it's basically because the columnar way of storing data is great to aggregate data quickly, which wouldn't be good, of course, for OLTP. Interestingly, one of the technologies that we started to support recently is MariaDB column store, which is based on MariaDB, which is for OLTP. But on top of it runs the column store storage engine, which actually forms a cluster. Well, if you want, it is optional, of course, but it can run on multiple nodes, and it can form a cluster. And it will be a cluster of columnar databases for analytics built on top of an OLTP technology. And it's a very interesting mix if you already use MariaDB or maybe MySQL, because it will allow you to move data much more easily and reliably between the data sources and the data warehouse. But anyway, let's go forward. Let's move forward. I mentioned that the data warehouse is built using a standard way of designing a schema, and this standard way of this standard design is actually is for running analytical queries more quickly. And in particular, what I mean is that joins, certain types of where, and group by will be quick. And I will show you later why. Well, actually, I can start to show it now, because what you can see here in this slide is the typical data structure used in a data warehouse. It's called a star schema because, well, I hope you can see my cursor. Anyway, you can see a central table, which is the center of the star, and it's called a fact table. And then you can have multiple tables. which are the points of the star, and they are the dimensions, right? And of course, each dimension is linked to a fact table with a foreign key. Well, it is a logical foreign key. It doesn't really have to be a real foreign key. It's up to you, but usually foreign keys are not really used because they slow down a lot the loading of data. Anyway, this is the structure. As I said, it's called a star schema, and the most basic concepts are, first of all, a star represents an event. Okay, an example of an event is customer buys product. Okay, it is a business process. Okay, it is a business event that happens, and you want to get more information about it. A dimension is a characteristic of an event which we might use for filtering and for ordering. And in this case, could be purchase date, delivery date, product name, product category, customer city, where the customer lives, or more, of course. Which exact dimensions you are going to use? Well, it depends on your business, on what the business people are really interested in knowing, okay? Don't add dimensions because theoretically they could be useful. Don't add them because you think that they make information more complete. Add them because you discuss with business people and they say that the dimension is useful. The grain is actually how specific these dimensions are. Grain or granularity. Okay, actually the grain term is used, but granularity could be clearer probably. And basically, it determines how specific the values of dimensions are. Okay, for example, the time dimension should be a date or just a month. The place where the customer lives, should it be the postcode? Should it be the city, just the country? It depends what you want to measure. Actually, in many cases, you will have multiple star schemas with multiple dimensions that contain theoretically the same data, but in practice, they have different grains. Okay, so you might have a dimension for, you might have a star schema where the granularity is date and city, and another star schema where the granularity is month and postcode. Okay. Anyway, the other concept is, of course, facts. And facts are measurements that we take and we want to aggregate and analyze. Okay. For example, it could be cost of the products that have been purchased, or discount that have been applied, the number of products bought, or more stuff. In practice, they are almost always numbers. There is an exception that I will tell you later. Now let's see a bit more about how to design a data warehouse. And well, designing a data warehouse is a technological activity that requires some business knowledge. But is it true? No, false. False, false. I hope you noticed the word false on the slides. It is the opposite. Designing a data warehouse is a business activity that requires technical skills. Okay, because you have to understand the business, its processes, and what needs to be measured. And then, of course, you need the technical skills to make it true, right? To make it happen, to actually design the physical tables that will contain this data. And there will be data engineers who will actually build pipelines to move the data actually every day, every night, or whatever. But it's important to remember that the design itself is essentially a business activity. And no decent data warehouse can possibly be built without understanding the business itself very well. And not any business, but of course your business, the business of your company. The design starts by identifying business processes that you want to have more information about. And some examples of processes or events are a customer buys a product, as we mentioned before. A Google ad campaign runs, okay? A courier delivers a pizza. And we might want to measure different stuff about each of these events. Well, of course, in the case of Google Ads, we want to measure how much we are spending, how much money is returning from our campaign. I don't know, maybe the number of clicks, stuff like that. I don't know if it's interesting or not. Anyway, yeah, this will be the events. And in the last case, well, obviously it applies to companies who do delivery. And in that case, sorry, in that case, you will want to know things like how much the customers spend, how much you spend to deliver the pizzas, how much time it takes, whether customers are happy or not, stuff like that. Okay, and then you will identify the dimensions. But anyway, one thing at a time. Because actually, this is not strictly related to data warehouse design, but well, I wish it was considered strictly related, because I think that when you design a data warehouse, you should also write a dictionary of the business terms, because everyone should understand those terms. They will be used in the data warehouse. You want to know what you are measuring. You want to know what each dimension means. And this might seem trivial because they are English words, or maybe even words in your native language. But the meaning a word has on Oxford Dictionary is not the meaning it has for your business. Okay, there are more complex definitions that are related to how things work in your company. And in many companies, actually, different teams use the same terms to indicate different things. Sounds crazy, but it happens. It happens very often. And of course, when you build a tool for exploring the data, everyone should have the same understanding of each dashboard. Then you should discuss every event with all the people who need information about it. And typically, this means that for each event, you will discuss with people from multiple departments or multiple teams. So gather them in a room, sit with them, and find out what exactly they need to know, again, which facts they need to see, and which dimensions they need to use to filter or aggregate data, and what grain they need for those dimensions. Well, actually, in this slide, I'm repeating the same things, but anyway. And then modify the event statement by adding the time when it happens and the dimensions that affect its graying. So the first example was a customer buys a product, and okay, this can be an event, or it can be one version of the event, and it's totally fine. Okay, if you do that, every row in your data warehouse will represent a single purchase. You might also have something like customers buy products in a day in a city, and it means that you have rows that aggregate data. Okay, data are pre-aggregated. This means that you are not importing into the data warehouse every single transaction. You are just importing data already aggregated, and it's fine if you don't need to see every single transaction, every single purchase. It's fine. It's a good idea to aggregate data. You will reduce a lot the size of the data warehouse, maybe even the complexity of the queries. Okay, and the last example is just the same example with a different grain. So customers buy product in a month instead of a day, and in a country instead of a city. Okay, so it's even more aggregated in this case. But you can also have multiple versions of the same event. You might have all these three tables, or actually all these three star schemas, and it's totally fine because this could be needed for performance reason, because aggregating data on the fly can be slow. When you have really a lot of data, maybe running certain queries can take hours or even days. Yes. So if you can pre-aggregate some data to avoid waiting forever for a query, I mean, it will help you a lot. It will help analysts a lot in their daily job. And then let's see a bit more about the dimensions. As I said before, dimensions are the criteria that will be used to aggregate data, filter data, and order data. Okay, and by data I actually mean the numbers or the facts. Okay, so some examples are average amount spent, and I mean this is the fact part of the information, right? The average amount spent by customers over 40 in 2024 in France, aggregated by store city and date. So the second bullet is the filter, right? Or in SQL, it's the where clause. So amount spent by customers. So customers will be a dimension, okay? And a dimension is not just a column, it's a table. And I will highlight this a bit later. It's a table, and this table has some additional information. So I can actually start by filtering customers by their age, and then I will find the match in the fact table. In 2024, so when the purchase happened in France, so in which country the purchase happened. And then I can aggregate this information. So it's a group by in SQL. I will aggregate by store city and date. And this is what probably the query will return, more or less. Or maybe I simplified a bit, but don't focus on what is missing. Just focus on what we have. And actually, here I have a question for you guys. And my question is, if this is what we want to see, if a data warehouse anyway is not a normalized database, okay, it is a data structure built for analytical queries, so to make analytical queries faster. So if all this is true, why the hell can't I just load data into this table? Why can't I have tables like this and load data into here directly? And yeah, I really encourage you to answer maybe in the webinar chat.
This is the Q&A section where you can answer.
Great. Let me know, Stacy, if some answer appears. I'd be really curious to interact with people. Of course, if no one knows that, it's fine. I will explain it. But you know, I like to discuss, to find out things together rather than imposing some universal truths.
I don't see the answer so far. Maybe we need to repeat the question.
Well, the question is just why we can't have a table that matches this query exactly and just load the data into it. But, well, if no one answered, it's fine. Maybe they just don't know, or maybe they are shy. I don't know. In any case, there are several reasons, and they are here. So with this simplistic design, first of all, adding dimensional columns will be a pain, because you have to consider that a dimension can be small or it can be big. It can be even very big. But in all these cases, it will be very small compared to the fact table, okay? Because a fact table could even contain all possible combinations between all dimensions in theory, right? So it's much, much bigger than every dimension. And if you have to add columns. Oh, cool. Well, let me continue to give you my answers, and then let's see what people wrote actually. So let me finish here, and yeah, adding a column to such a table would be a pain. Adding column to a dimension table, it's fine. It's actually relatively easy to extend a dimension with some additional information later. Also, loading data into the table itself is harder. Okay, because if I have several dimensions, I can populate every dimension separately, and then I can load the facts. But if I have to do it all together, the process will be much more complicated, and probably it will even frequently fail, because I'm trying to do very complicated stuff. Also, with this design, I can't query a dimension alone. So, I mean, I can, of course, but the performance could be terrible. For example, if I want to get a list of the countries, of course, I have to eliminate the duplicates, and that's why it could be very slow. And we can't get a list of things that didn't happen. For example, I can't see that a certain store, a certain date, didn't sell anything. Okay. I mean, yes, I could see it, but I will need a very complicated query, and it will also be very slow. So this is a type of information that needs a proper star schema. But anyway, these are my answers. But yes, Stacy, if you can read me the attendees' answers, I'll be very curious.
Carl says, supposes that this is because data warehouse doesn't ensure the integrity of the data.
That is partly true. It doesn't have to be the case. Some data warehouse technologies do have features that ensure the integrity of the data. Other technology don't have them at all. And maybe they miss foreign keys or unique indexes or other stuff. So basically, with those technologies, it doesn't matter how you ingest data. In any case, you will be responsible for making sure data is correct. So that is a case where, I mean, that integrity is something that is mostly for the application itself. The application that inserts the data, or actually the ETL process. Any other answers?
Yes. The Caroline's supposition is this may not be the only information you want for the data you have. You could, but there may be more questions later.
Yes, it's true. I didn't include it into my answers, but it's definitely true. You might want to aggregate the data in different ways, and in that case, you would have to build a different table. But maybe it's not a universal answer, because in some cases maybe it's not true. In some cases maybe data are aggregated in a single way, and in theory doing it fast could be more important than flexibility. But then you would have all these other problems. So yeah. Okay, cool. So let's continue. Thanks for answering, guys, and thanks, Stacy, for reading the answers for me.
We also have a raised hand here.
Cool. Yes, let's see.
So let's. I will allow Vishal to talk if he wants to provide a question or add something. So I think you can talk now.
Hello.
Okay.
Hello.
Yeah, please tell me about the aggregate data. What you told before that, sir. Aggregate.
Sorry, I don't hear you very well for some reason.
Aggregate. You told na aggregate before. Some aggregate about.
I have troubles hearing you. I'm sorry. Could you
Okay,
maybe write?
I think there is something written here. Can you please tell me about aggregate, what you told before? So this is the question.
Yeah, sure. Well, maybe I will have some more slides later about this, but basically, I'm not sure what you want to know exactly, but I can tell you, well, of course, in general, queries for data warehousing are for aggregating data, right? So you want to know, for example, how many purchases in one day. So you will have to use the count function in SQL, or you might want to know the average money spent or the total money spent in a certain day. So you will use functions like sum or AVG. And of course, to aggregate data, you also have to decide how you aggregate it. So you will use group by clause. There is a slide later. Actually, I can anticipate. Actually, okay. I'm sorry if we move a bit forward and backward, but I want to answer your question. Basically, this is a typical query that we might want to run over a star schema. As you can see, we have the fact table, we have the dimensions that we use, we have some filters, because typically you also want to filter the data, you don't want to aggregate everything. And then you have a group by. This example is a bit simplified and actually even incorrect, because in the select clause, we should see some aggregation, but to simplify things, I just listed all the columns. But in practice here, we might want to have something like, I don't know, for example, we might select the date and the city because they are the aggregating columns. And then we might have, I don't know, count, which will be again the number of purchases that have been made by date and by city. Or we might want to sum the money spent, or show the average, or even the maximum and minimum if they have meaning for us. So yeah, this is what I mean by aggregating the data. Make sense? I hope so. Anyway, let me go back again. Okay, guys, I'm not sure if there are more questions, but sorry, guys, I have to proceed now. Otherwise, I won't be able to finish all the topics. And then after that, of course, there will be time for more questions if you want, right? Anyway, again, this is the typical star schema. And if we look at it, dimensions usually have these characteristics. They are stored in separate tables. They are denormalised. So this means they don't follow the normalization forms, the normal forms of a database that we, or some of us, studied at school. So for example, hierarchies are represented by repeating the data. Okay, you will have, for example, if you have I don't know, a country and then city, we will have France repeated many times, and then we will have Paris, Lyon, Nice, and blah, blah, blah. Okay, so it's not normalized. The dimension is basically designed to be stored in the same way that is returned by a query. dimensions have an ID that should be unique to the data warehouse and should have no other meaning. So, for example, it shouldn't be a code that has some meaning for us. It shouldn't even be the ID that comes from MySQL or from Postgres. It should be generated in the data warehouse itself, because if we rely on the fact that it has a match on the original data source, we might have problems in the future, because maybe in MySQL we have ID 25 that represents a certain employee, and then the employee leaves the company, and maybe at some point, for some reason, a new employee appears with the same ID. This is just one example, but it's an anomaly that can happen, and it would basically mess up our data warehouse. So the IDs should be generated in the data warehouse itself. Human readable information is stored in other columns, and these columns should be indexed. Okay, at least some of the columns that we might use for aggregate data or for filtering data, these columns should be indexed. But we are not going to talk about query optimization here because it's a completely different topic. Maybe we will make a different webinar on that one day. Anyway, so here's an example, right? This is a hypothetical dimension called dim city. It's a sort of convention to start dimension tables names with dim underscore. So as you can see, we have columns that are kind of hierarchical, okay? Continent, in a continent, we find countries. In countries, we find cities. And, basically, Europe is repeated many times. Italy is repeated many times. And they are repeated once for every different city. Oh, but actually, there is even one more column in the hierarchy, which is language. Because in some cities, more than one language is talked. Well, we might have things like local name, which are basically accessory information that we might use for filtering, or we might use just to show them in dashboards. Okay, this has nothing to do with aggregating data, but I mean, it's a potentially useful human readable information. And then in this case, we have a number, but this number is actually part of the dimension because it's the population of the city. Well, probably it should be rounded following some rules. So, for example, it would be easy to read it, or it would be easier to even filter in it or group it. Anyway, it's a characteristic of the city. Okay, so because it is a characteristic of the city, it is definitely a column for the dimension for the dimension table. You might object, but what if we want to do some type of strange calculation? Maybe we want to aggregate the population. Well, for example, maybe you want to know the average population of the cities where we have some stores. Okay, in theory, we might need to do something like that, but to do it, we will build a separate fact table with the population of the city. So it's not very frequent, But it can happen sometimes that the same information is a column in a dimension in some contexts and effect in some other contexts. And then let's talk a bit about facts, because facts are not trivial neither. A fact table usually contains references or foreign keys to dimension tables. Again, usually in a data warehouse, foreign keys are not used because, again, they slow down the process of ingesting data. But, again, it is not a universal rule. It's up to you. In any case, we have a foreign key or a logical foreign key that points to a dimension table. And then we, of course, have one or more numeric columns, which are the facts. And here is an example of a fact table, which is called fact in-store purchase. Again, it's a convention to start fact table names with fact underscore. And then there's a lot of stuff to notice here. I will point out just a couple of quick things. The date is actually a number because this simplifies some queries, simplifies even the ATL process. So it's better if a date is represented as a number. Okay, but this number is human readable, right? Because even if it's a number, it's still, we look at it as if it was a string. Okay, the first four characters are the year, following two characters are the month, and the final two are days. And then we have an ID for the country, an ID for the city. Oops, sorry, an ID for. Oh, no, sorry, this is a date, not an ID. The date of birth of a customer, which actually shouldn't be here, but I will get back to this in a second. Prod count is actually a fact. It's the count of, it's the number of products that have been purchased altogether with a single transaction. And then we have the total price spent in that purchase, okay? The sum of the product's price. Customer date of birth shouldn't be a column here, actually, but it happens. Sometimes, no, I mean, sorry, okay. What I was going to say is true, but it's not completely true that it shouldn't be a column here. Actually, it should be a column here because, I mean, we have a date dimension that is referenced twice, right? We have the date of the purchase and we have the date when the customer was born. So they both point to the same dimension table. But it's still worth mentioning that sometimes there will be no table for this. If there is, basically this human readable number is the ID of a row, okay? But sometimes people just avoid having a date table, which is not a good idea if you ask me, because it will be harder to find out, for example, the day of the week, okay? If you don't have a separate table, it's really hard to find out the day of the week. But maybe they think they don't care, or they just want to simplify things. So you can actually have a dimension that is just a column in the fact table. In my opinion, you shouldn't, but again, you could. And if you do that, it's called a degenerated dimension. Well, I already shown this query before to answer a question from Alejandro, I think. So I think I don't need to repeat it, but well, apart from the lack of aggregations here, I think it's pretty standard query. And one thing it shows is that it's easy to write, okay? I start by listing the tables. I start from the fact table, then I add the dimensions. If I use the same column names in the fact table and in the dimensions primary key, I can use the natural join syntax, so I don't have to add on and then a condition for the on. And then I list the columns that I want to see, and then I add some filters, in this case on the date, on the weekdays, on the country, and on the customer's date of birth. And then, of course, I add some group by or order by. There are 3 types of fact tables, and they are called transaction fact tables. And the typical example is customer buys product, or here actually I wrote our company buys products. Okay. We register a single event, okay, that happens, and that has a matching row in our table, in our fact table. But then we have periodic snapshots, fact tables, and periodic snapshot is something we measure regularly. For example, monthly inventory, okay? And in this case, in the first fact table, we will have every single purchase we make. So if we have, I don't know, 100 tables in our warehouse, it means that we probably have made, I don't know, 100 purchases here. Okay. But the periodic snapshot is just a measurement that we take periodically. So periodically, probably there will be someone who counts the products in our warehouse and will register this number. So we will have a row for every month in this case. And then there are accumulating snapshots, which are for events that consists of multiple steps. For example, a courier delivers a pizza. Why is it multi-step? Well, because first the customer places an order, then the pizza is ready, then the courier collects the pizza, and then the courier arrives at customer house. So in this case, we might have 4 steps. We don't have to. It depends if we are interested in every steps. But if we do so, we will have 4 different times registered in our fact table. And this can help us to find out which steps took how much time. Okay, so we can know that typically a delivery from point A to area B will take, I don't know, 10 minutes, for example. Okay, we can take measures, we can get information like that. There are also factless fact tables. Basically, they are a special type of fact tables, usually transaction fact tables, actually. Their characteristic is that they don't have any fact column. They have only dimensions. and they are basically Boolean. Okay, they indicate that something happened. Okay, if I have I don't know a student column and a date column, if I have a matching row, it means the student A took an exam yesterday, for example. And if the row is not there, the student didn't take an exam yesterday. It is not a realistic example, but sorry, it is what I had on the top of my mind right now. But you get the point, right? It indicates events that happened, and by extension, it also indicates events that didn't happen. Okay, here we have another example of a fact table, which is actually a factless fact table. And it's also a transaction fact table. Okay, and as you can see, we have a column for the date. I already explained you the format. We have a column for the customer who made a call to the customer support, and operator ID, which points to an operator dimension. So we know that customer 8 blah 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 called on this date, and operator 927 answered the call. Okay, we might have some facts about it. Actually, we might register the length of the call, some kind of metrics that should indicate if the customer is satisfied, but it's also totally legit that we don't have this information, and then we will only register that the event happened. And then let me spend some words about time dimensions, because they are very important, and basically every star schema has a time dimension. So general rules are have one dimension for the date only without time. Okay, sometimes you don't need time at all, but if you need it, it should be a separate column. The primary key, again, should be an integer in the form 4 digits for year, 2 digits for month, 2 digits for day. And then you add columns for any information that might be significant for us, like year, month, month, day, so day of the month, day of the week. If it was a work day in our country, we might have this information for multiple countries if it is important for us. If it was a leap year, but we might have many more information. For example, if our business is closed the first Friday of every month, we might have one column which indicates if that day is the first Friday of the month. Okay, so again, I can't give you a structure for a universal date table, because it's really bound to the business logics. And then the next column, as I said, is the time of the day. And again, it doesn't have to exist. It should exist if it makes sense. If it exists, the primary key should be an integer that is in the format hour, minute. And then you will add separate columns for hours, minutes, and any other information you might need. For example, if it is a working hour or not, if it is lunch pause or not, or whatever. Depending on your needs, you might want to add a row for every minute. Okay, so you will have a row for every possible time of the day. Or maybe it doesn't make sense for you, and in that case, you might have just a row for every hour, or maybe for every half an hour. Or you could have it only for working hours. It really depends what you want to store in this table. Let me spend also a couple of words about constellation schemas, which is just a fancy term to say that you usually have multiple star schemas, okay? Multiple stars form a constellation. So, but in a constellation schema, you should be careful about a couple of things. You should have conform dimensions. This means that typically some dimensions are used by multiple fact tables. Time is the date is the obvious example, okay, because every fact table should have a date, probably. I never saw an exception, at least. To do this, you should actually reuse the tables. You shouldn't duplicate them. Add more columns if you need to, but don't duplicate the table, because the process of loading data will become more complicated if you add unneeded dimension tables. Again, this is called conformed dimensions. Two stars might also represent the same data with different grain or different granularity. So some facts are present in multiple fact tables. Those facts should have the same name and the same, the values should be also consistent, okay? For example, in an aggregation, maybe you want to store, I don't know, how many times a purchase was made per minute. Okay, if you use it in one fact table, use it in other fact tables too. Don't have purchase per minute in one table and purchase per hour in another table, because again, this will complicate the data loading processes. And this is called conformed facts. Okay, so the meaning and the name of the facts will match and is reused every time it's needed. But we talked about the stuff, but data warehouse is a complex matter. And we definitely didn't talk about all important topics. We left out a lot of stuff, and there was no way we could talk about everything in a 1 hour webinar. So some things I left out are, for example, how to represent a dimension which is an invoice or a bill of lading, because if you think about it, it's not trivial, because one invoice contains multiple items, each one has a cost and blah, blah, blah. So if we want to measure facts for each invoice, you have to think how to do it. I left out how to represent dimensions that change over time, because okay, we have a store dimension. Today we opened a new store. I can't just add a row, because otherwise, if you make a query about the past, that row might appear, but the store didn't exist yesterday. So that is something that should be took care about. I didn't talk about role-playing dimensions and other dimension types that are not always trivial. I didn't mention data marts or data lakes, but they exist, and sometimes they have a relationship with the data warehouse. I didn't talk about a maybe separate but very, very fascinating and important topic, which is using a data warehouse to feed machine learning and a lot of other stuff. Okay, so if you are interested about these things, contact us for a training and we will be happy to teach you about it. Or if there is still time, use this time to ask me some questions. I actually don't know if there is still time because I don't know how long I talked.
I think we have spent a bit more time than expected, but probably we can handle a couple of questions.
Sure.
So let's see if there are questions. Can you please explain what timestamp means?
Sorry?
A bit unrelated question. Can you please explain what timestamp means?
Timestamp? I don't think I mentioned timestamps here. It's just a way to record the exact moment in time, but usually it is the number of seconds that elapsed since the beginning of 1st January 1970. But again, I didn't mention it. The most similar thing I talked about is this way to store date, but it's not a timestamp. It's a number, but you should look at it as a string. Okay. So again, in this case, first four digits are the year. So you can read, as a human, you can read 2024, and then you read the month, which is 2 February, and then you read today, which is 1. Okay, so it's a number, but it's in a format that is human readable. It's not a timestamp, by the way. Anything else?
Let's see if we have more questions. Just type them in the Q&A section if you have them. Let's wait a bit.
Sure. Or maybe people are just tired because I talk too much, which is legit.
The topic is quite complex. So.
Yeah, it is. I try to summarize, but yeah.
So I don't see if we have any other questions. Just thanks.
Oh, cool. You're welcome if you wrote thanks. Well, if there aren't more questions, maybe we can let them go.
I see that Carl is asking something.
Oh, sure.
Why should we create new IDs in the data warehouse and not reuse IDs from the OLTP schema?
Because in ID in an OLTP schema, at least in theory, could change, or it could be deleted and then reused for a separate row. So using it for the data warehouse would be a problem. I mean, these events, a change of an ID or a deletion and then a recreation, would create inconsistencies in the data warehouse. But it shouldn't be a problem because we can just use auto-incremental IDs in the data warehouse. Of course, the problem becomes how can we match the information in the data warehouse from the rows that generated it. But that's another complex matter because it depends from the definition of the object that we are representing. For example, what is a customer? What identifies a customer? It really depends on the business logic. It could be a certain device, for example, a certain phone. This doesn't really match the reality. In reality, the same phone can be used by multiple people. But maybe for the purpose of our data warehouse, it doesn't matter. Maybe we don't want to know if the phone was used by the dad or by one of his children. We only want to know that that phone made a purchase. Okay, so or multiple columns actually could identify a customer. For example, I don't know, if we are a food delivery company or a delivery company in general, a customer could be identified by a city and an email. Okay. And again, it doesn't match the reality because if a person travels, we will see multiple customers. But maybe for our statistics, for the statistics that we want to see, maybe it's totally fine. Or maybe it is actually what we want to happen. So that is why at the beginning I said that we should write data dictionaries, and the definitions of words that we see on the Oxford Dictionary or other English dictionaries is not the definition of our business terms. They are completely different concepts. And in our case, this often means that a customer in the data warehouse doesn't match necessarily a single row on our OLTP MySQL database. And even if it does, we might want to use different criteria to identify that customer. I know that instead of clarifying things, my answer probably added confusion, but it's because, again, a data warehouse is complex by nature. And this is an aspect that I didn't plan to talk about, but yeah, it is important, and it brings more complexity.
Let me check if we have more questions.
Mm-hmm.
Can you please tell me about truncate and delete? Because most people are using truncate. Why? Not sure if we're talking about this either.
I will assume that you mean in a data warehouse only. In a data warehouse, usually you don't delete data. and you don't empty tables. You keep adding more data, okay? You add data this night, and the data will remain potentially forever. And the following night, you will add more data, more recent data. You don't delete data. But if you have to do it for some reason, well, you might, for example, rotate data and delete the oldest data you have in your fact tables. But you don't empty the tables again. Something you could do to make this rotation faster is partition the fact tables. Partition the tables by time, and then make sure that every partition contains, for example, 1 year of data. And when it is time to delete the oldest year, you can do it by dropping the oldest partition. It will be fast.
Okay. I think we have a very strange question, like binary means what? I think it's a Wikipedia question.
I really don't understand what it means here.
Yeah, it's strange.
I mean, if you can clarify, I don't remember mentioning anything binary.
Yeah, I can't remember anything like this either. Let's check if we have more questions. I think we've spent like 20 extra minutes, and probably we need to wrap up.
Yeah, definitely. We want to let people go. But I hope it was useful for everyone. If they're not asking anything anymore, we can just say bye, I think.
There is a clarification. I'm asking about binary and alias, how they are used.
I mean, in a data warehouse, I don't think you can find binary data.
Okay. I think this is all for now. So I think since we don't have any other questions, let's wrap up. Thanks everyone who is still with us for attending today's webinar. Surely thanks to Federica for covering this complex topic. And we'll send. Oh, sorry.
Thank you for listening.
Yeah. We'll send the slides and the recording to all of you via email. And our next webinar will cover the integrity features of relational databases. And it will happen on July the 10th. And of course, you are all invited. I'll also share with you the link if you are interested in an email. And for now, have a good evening, everyone, and goodbye.